Hey AP Stats family, we are in the last section of our last unit. We're starting section 12.2, transforming to achieve linearity. So after this section, you should be able to use transformations involving powers and roots in order to achieve linearity. You're going to be able to make predictions from a least squared regression line involving transformed data. You're going to use transformations involving logarithms, you remember those, in order to achieve linearity. And you're going to determine which of several transformations does a better job. Let's dive in. Now, while we love data that is linear, it is not realistic to expect that all data is going to have a nice linear relationship, right? Sometimes it has a different relationship. There are going to be different types of nonlinear graphs. We're going to be focusing on two of those today, power model and the exponential model. I know your notes are in black and white, but you can kind of see how we have these different functions. The red one on the top is a linear relationship, right? It's just 50x. The blue one is a power model. X is raised to some power. In this case, it's a cubic raised to the third. And then the last one, the green one, is what's called an exponential model because the variable is in the exponent spot. Now, what are we going to do in order to transform our data? Let me tell you. Oops, how do I go back? There you go. We cannot do a least squares regression line unless we have a line. So we're going to have to transform the data by applying a specific function that will transform it into linear data. So, quick example before I talk about the rules. What does the under 5 child mortality rate per 1,000 live births tell us about a country's income per person, measured in gross domestic product per person, adjusted for purchasing power in that country? Here are data from 14 different countries back in 2009. And you can see here, there is a scatter plot of that data. While there is a negative relationship, a negative association, it is clearly not linear. It's pretty curved. So what would happen here? If the relationship between two variables appears to follow a power model, for the example we were just looking at, I think it was to the power of x to the -1, because it looks like both the x and the y axes appear to be asymptotes. So I think it's x to the -1. Different powers could be like x squared, x cubed, even cube roots or square roots. Those are all different powers. There are two different transformations that you can do in order to linearize the data. You can either raise the power or raise the values of the explanatory variable x to that power of p and then look at the graph of that, or you can take the whatever root of the y values and then look at that graph. Of the different methods we learned today, this is my least favorite, this option for using powers and roots. However, I want you to be aware that it exists, and there's sometimes it works out nicely, other times not so much. So we're going to look at two examples today. So looking at our first example, we talked about how it's clearly not linear. This first scatter plot right here on the left, bottom left, is the original data. Since we can approximate this graph as something to the -1 power, you can linearize it by either doing 1 over child mortality, aka 1 over your x's compared to the income, or you can do child mortality compared to 1 over the income. That's what these second two scatter plots are showing you. The 1 over child mortality is showing you here in the middle, and the 1 over the income is showing you at the end. Clearly, they're much more linear now. So what we're going to do is we're going to calculate the equation of the least squares regression line for the transformed data. We're going to make sure we define our variables, and then we're going to pick, actually I'll show you on both. We'll use those regression lines to make predictions about what the income would be for the U.S., where the child mortality rate is 5.87. If we want to calculate the equation of the least squares regression line for our transformed data, we need to have our data in our calculator. So if you flip back to the front, the first page, you're going to look at your data right here, and you're going to put those into your lists, okay? I'm going to put my under 5 mortality rate in my list 1 for my X's, and my income in my list 2. My explanatory always is my X value, and my response is always my Y value. So go ahead, pause this video. If you go to edit, or if you go to stat edit, that'll be the place where you plug in your data. So go ahead and do that now. Once you've plugged in your data, there are a couple things we need to calculate. So we don't want to get the least squares regression from this data as it is, because it's not linear. But look how much more linear it is once I did these transformations. So for this first one, I'll call this transformation number 1. And then this will be number 2. Just so we can keep them straight. In order to do transformation number 1, I need to have not the actual values of the mortality rate, but I need to have the inverse of that, right? 1 over it. So my mortality rate data was in my list 1. So I'm going to calculate list 3. Notice how I went up here and I highlighted L3. What I'm going to hit is 1 divided by, hang on a second. We're going to do 1 divided by list 1, since that's where my mortality rate data was. And we get all of these values. You don't need to write them down anywhere, but now we're going to use it to make a least squares regression line equation. So if you remember, if you go back to stat and you go over to calc, option number 8, we have our X values, quote unquote, in list 3 right now, because that's where we transform the data. And the original list 2 is where our Y's are. Your frequency list should be empty, and we're going to hit calculate. And it gives us our y-intercept and our slope. So for transformation number 1, our y value is income. So I'm going to do, instead of using x's and y's, I'm literally going to write out the words so it's clear. Remember to put a hat over my income. And then that is 868.2913. I'm just going to do 4 decimal places. Why not? Plus 104867.9548. And then here's where normally I would put an X here, or mortality rate, but it's actually not that. It's 1 over it. So this actually goes over my mortality rate for those under 5. Okay. For transformation number 2, I need to have 1 over my income. So I'm going to go back to my stat, edit. In list 4 now, I'm going to do 1 divided by list 2. The way I do that, it has second 2. And I hit enter, and it gives me all of these nice tiny little decimals. I'm going to go back now and do another regression equation. I want to use my original X values, but now I'm using my transformed Y values, which I put in list 4. And I hit calculate. And notice how it's negative 5.94, but it says e to the minus 6th. That means it's a very, 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 very small decimal. Okay? So my transformation number 2 is not just income. It's 1 over my income. And this is prediction, so it's under a hat. I have negative 0 point, and it's going to be 5 zeros. 1, 2, 3, 4, 5. Followed by, let's say 5, 9, 4, 8. Sure. Plus 0 point, again, 5 zeros. 1, 2, 3, 4, 5, 8 to 9, sure. And then I didn't change my X at all, so this can just be my mortality rate. And these equations are given to us, and they're shown here. That would be the line of best fit for these two scatter plots right here. Now we want to do a prediction. Because my data has been transformed, my prediction might not be super close, especially just because we did an estimate for how I thought the power equation was, the power model. So it's okay if it's going to be a little different. So if we're using option 1, we want to know the income for the mortality rate of 5.87. So that's my X, right? That's my mortality rate. So I'm going to plug it back in up here. So I would do 868.2913 plus my slope. But now I need to divide it by that mortality rate. That's going to give us a value when you plug that in your calculator, approximately 18,733.36, right? This is money. Now, if I did it for transformation number 2, it's going to be a little bit different because you're actually getting 1 over your income when you plug that value in here. So you end up getting a really small number. So 0.0042715.3-ish. So in order to get just income, I need to do the inverse of that. So the income, my predicted income, would be 1 over that answer. Which gives me approximately 23,410.8, let's say 2-ish. Again, notice how these are off, but that's okay. I didn't expect them to be super close or perfect, especially since I was making a guess here. Now let's look at our next example. This one's going to be a better one. And there's really good examples in the book as well as on the supplemental videos that I linked in our playlist. The Jurassic Toy Company produces 7 models of their stuffed Brachiosaurus. Sure. Each of the newer 6 models scales up to the original successful model. The table gives for each model the volume of compressed stuffing required in cubic inches. Oh, I love this because it basically told me what the model is. It's cubic, aka to the 3rd power. So my X here is my scale factor. And my volume here is my Y. So in order to transform this data, because if I were to graph this data, it's not going to be linear. If you want to see it, what it looks like. So if I go to Stat, Calc, let's do 8, and I want to put that there. We want to get that equation, and I can put that in my y equals and graph it and see how it's not linear. But I can transform it. So you can either do raise your x to the same power as what you think the power is, or you don't have to do both, but you can do one or the other. You can do that root. So we would do the cubed root of y. So what I'm going to do in order to get my equations for my least squared regression line, I'm going to show you both methods. Again, you don't have to do both, but you can do one or the other. And I'm about to run out of time. We'll pick this up in the next video.